Okay, thank you very much for the introduction, and I also thank the organizers for giving me the opportunity to share something about my research here in this wonderful city of Baku. I really appreciate that. Actually, it's a bit hard to condense my research within 15-20 minutes. I try to do so, so I want to talk today about non-equilibrium polymer systems. So polymers are long molecules, chain molecules. They can be water-soluble, they can be non-soluble in water, and you can even combine different chains into one molecule, and then you have chains or molecules which are partly water-soluble, partly non-soluble. So the insoluble part wants to get rid of water contacts, and that happens by assembling a number of these molecules into these micellar entities. And these micellar entities can have different structures, as you see here, spherical micelle, worm-like micelle, a vesicle, or even aggregates of vesicles. So this is one part I want to talk about today, and the other one is about electrochemistry. So the idea is just to use a switch on at the wall and to induce changes in properties of your system, polymer system. So these two things I want to talk today. So after addressing in a short non-equilibrium system in general, I want to talk about an electrochemical solubility switch, and then how we can use micelles in a non-equilibrium state to change the properties upon request. So let's start here with this schematic energy landscape, which is taken out from a review from Hermann's, and it tells us if you are in the global minimum of this energy landscape, that's the most stable configuration, the most stable structure in your system. So here you are in equilibrium, but apart from that, you can have side valleys where you are maybe entrapped and you cannot get out easily. For example, in this case, you need to overcome a high barrier, and that's not easily possible unless you melt down your peaks, and then you can have this state where you, by just using small deviations from metastability, the whole system will run towards the equilibrium state. And at the same time, major property changes will occur. Now, I'm interested in these red dots here, but recently this dot was addressed in literature very much. It's about the dissipative non-equilibrium self-assembly. That means you need to provide fuel, you need to push in energy all the time in order to keep that state, and once the fuel is out, then the whole system runs towards equilibrium. Now, the editors of these reviews, they state that chemistry has for most of its time focused on the synthesis of systems that are stable. This makes sense, as stable molecules and materials are easy to make, store, transport, sell, and utilize. Further, non-equilibrium states and associated kinetic processes have, of course, also received attention, but usually only as transient regime in the synthesis and preparation towards the final equilibrium state. So this is the state of the art, but it tells us there's more to come. So we want to address that, and I start with a very simple example. It's a very poor man's mind depiction here, what may happen to, for example, now we don't have classes here, but what happens to a glass or glass window on long time scales. So glass is a non-equilibrium state of material, and it also tends to minimize the potential energy. This one aspect of the non-equilibrium state of glass. It wants to minimize its potential energy, wants to flatten out. And I take this this example actually from some observation in cathedral windows where the bottom of the windows are thicker than in the top. So people argued, okay, this might be glass flow on long time scales, so hundreds of years, the glass might flow. But actually, if you take a look into the physics, that won't happen in 500 years. That happens maybe in millions of years. So that's not the real reason. But there's another example which nicely demonstrates what can happen on different time scales. So this is a so-called pitch drop experiment. Some people call it the most boring experiment ever, because nothing happens except every 10th year, one drop of pitch of this black stuff here drops down. And otherwise, nothing happens. However, if you use short time scales and you have impact, the whole thing will splinter apart in thousands of pieces, so it's very brittle. So you have here different properties united in one system, and the idea is that we change between these time scales in a way, and we want to freeze a certain structure in a certain time scale by using plasticizers. But however, if we take the plasticizer away, we get the brittle state, and if we add plasticizers, we get the fluid state, which then can adapt to the equilibrium state easily. But once we freeze the system, we can bring the system to another conditions where it's not in equilibrium state, and then upon triggering, it will run towards the equilibrium. Now, I will explain that later in more detail, but here in this picture, there's also a battery, because that brings me to my next point, because we can use also electrochemistry to bring a system out of equilibrium. So if you all know that battery is a non-equilibrium system. So once you shortcut it, you will see that there's energy stored. So at the same time, you can charge a battery, you can bring your system out of equilibrium again. And so the system is only in equilibrium when the potential difference between the poles is zero. So once you have a potential difference, the whole system is a non-equilibrium state. So people use that, for example, for polymer systems, so-called redox flow batteries. It's just one example where they used polymers which can be oxidized, and then on the other side, polymers which can be reduced, and they put them on both sides of an electrochemical cell, and it's separated simply by a very easy or very simple dialysis membrane. So these two polymers want to react once they are charged. They want to react, but they cannot, because here it's the dialysis membrane. They cannot meet. And the only way to react is then that you shuttle electrons here via the LEDs, and you have then battery again, and once it's discharged, you can charge it up again. So this is one example how you can achieve a non-equilibrium state, and at the same time, we also adapt this principle for our system. So shortly, we use electrochemical stimulation for non-equilibrium properties, and then we use triggerable glass transition temperatures, so shifting the fluidity of the material by some means, and a pathway-dependent preparation strategy in order to achieve really non-equilibrium micellar structures. And this is done by using orthogonal triggers on glass transition and structure change. How do we arrange the structure change? We imply so-called thermoresponsive polymers, which change their solubility with temperature, and then you can also have a structure change when you change the solubility, and then you can freeze in your system by taking away the plasticizer, and if upon request, you can again make it more mobile, and the whole system will run towards equilibrium. Now let's start with the first part of the electrochemical solubility switch. So this is an older example where we used these star-shaped polymers with a cationic moiety, and we used here this polymer together with oppositely charged counterions, and these so-called ferricyanides, they interact strongly with this blue cationic moiety and makes it insoluble. However, the ferrocyanides, they don't interact strongly with the blue entity here, and it's still soluble. So by using electrochemistry, you can change the ratio of these two entities, and at the same time change also the solubility of the blue part. And if it's insoluble, you get vesicles in a very simple two-half cell setup. And indeed, we get these vesicular structures when we oxidize. So in this state, when we reduce, we go back to the unimolecular dissolved polymer. Now, this is a peculiar example because you change solubility at electrodes. And typically what you get is that you form films, film formation, you have electrodeposition at electrodes. So we wanted to know more about this system, and we did that by using a so-called rotating disc electrode. So this is the yellow part is the electrode, and it's embedded in an insulated cylinder, and the cylinder rotates. So there is liquid close to this electrode, and it feels also the centrifugal force of the electrode and is swept away. So that means new liquid needs to approach the electrode. So you have a very defined streaming profile close to the electrode here. Now it's an electrode, you can scan the potential. So with time you can increase the potential. And unlike in cyclic voltammetry where you get a maximum in the current potential curve due to depletion of your interface with electroactive species, you get here a plateau, a limiting current, which is due to the fact that you have a constant transport of electroactive material to the electrode. Now you can change your system and put also a ring electrode around the disk here, and then the products of the disk reaction need to sweep along the ring. So you detect the products here at the ring when you keep the constant potential and scan the potential at the disk, but the current's a little bit lower, and so this is given by the so-called collection efficiency, that you do not detect 100% of the products which have developed at the disk. Now, let's take a textbook example. So this is just ferrocyanide. You start here, you do a scan, you oxidize it, you get current, you produce ferrocyanide, and then you scan back, and the two curves are superimposing very well. Same true for the ring current. Now you add this polyelectrolyte again. So in a certain ratio, and then you start again scanning, nothing really happens, looks rather the same, but once you scan back, you see suddenly that there is a pronounced cathodic peak, this peak. And this peak tells us that the product of the forward reaction has been stored at the electrode and can be reduced now upon backward scanning. And if you take out the electrode, this is a platinum electrode, then you see that upon stopping here, there's a yellowish deposit of the ferrocyanide and the polymer complex. And if you reduce it again, you get a pure platinum electrode back because it is dissolved again. So we can now use these peaks to learn something about the deposition efficiency. So how efficient is our current or our charge which we transfer over the electrode to deposit the material at the electrode. So without going into detail, I would just mention some examples. This is the textbook example, no deposition, of course. Now we take the monomer, not the polymer, but just the monomer, no deposition. Deposition efficiency is 0. We take now a rather short linear polymer, polyelectrolyte. Then we see pronounced deposition. Now we extend the chain even further, then the deposition efficiency is lowered. It's smaller, it's decreased. Now we increase branching, it's even further decreased. And now you can, the reason for that is that you have more likelihood for intramolecular cross-linking than intermolecular cross-linking once you increase the molecular weight and once you increase the branching. So if you extend the series even further, more branching, higher molecular weight, you end up with so-called microgels. So these are particles in the size range of nanometers to micrometers, which are often swollen by the solvent. So if you want to know more about microgels, you can refer to this review. And I give just one example here where we used one peculiar microgel, which is permanently charged, positively charged. Now we can do the same game as before. We know that these microgels don't deposit at the electrode, but what we can do, we can adjust the equilibrium potential, we can oxidize, so these ferrocyanide will connect these chains, the whole polymer will collapse, the microgel will collapse, so a small size, or we can extend the microgels once we reduce it. So this can be done in a reversible way, and we don't see any signs of adsorption of these microgels on the platinum electrodes. Now, I want to turn to the last few slides regarding the micelles, the non-equilibrium micelles. So we developed together with Nick Warren, we developed a strategy to program the non-equilibrium state right away during the polymerization, right away during the preparation of the polymers. And this is done by so-called polymerization into self-assembly using a certain technique, raft polymerization, and the essence is that you have soluble polymer chains, so this dimethyl acrylamide. It's soluble in water, and you do the polymerization in water with two monomers which turn into a polymer which is not soluble at the conditions used. So that preparation conditions and then even at room temperature, it's not soluble, it's insoluble. So you extend this chain, and at a certain time, this insoluble chain will gather together into these small micelles. Now you extend the chain, these blue chains need more and more space, they cannot accommodate in this spherical domain anymore, and then you get worm-like micelles. And then even further, you get these vesicles. Hopefully you can see this is a hollowish structure. So that's well predicted by theory. That's what you typically get. But however, if you do the whole polymerization at low concentration of monomers and materials, then we see that we don't get this development, we get just only these spheres. And one reason for that is that at low synthesis concentration, there is a low amount of monomer, low amount of plasticizers, so there is hardly any mobility in this interior domains, meaning that there is no change for structural rearrangements, meaning you're trapped in this morphology here. Now, here, degree of polymerization of the insoluble block, synthesis concentration. At low synthesis concentration, we get only these spherical micelles. At high synthesis concentration, we get spherical micelles, worms, and vesicles. Now, we can take these vesicles diluted to the low synthesis concentration, meaning that we have the same polymer now, under the same conditions, but we have two different structures, two different micellar structures. And now we can play around with temperature. As I said, we can, temperature is a means to make this blue block soluble. At low temperature, at around 8 degrees, it starts to become soluble. Now we did a lot of small angle neutron scattering we get from these curved structural parameters of our system, so we can extract here the core radius, the length of the crafts, and so on. So here we start at 25 degrees, we cool down, nothing happens, we cool down further at 5 degrees, the whole system disassembles into unimolecular dissolved chains. Now you heat up, then you get small micelles, you heat up further, you get now worm-like micelles which are entangled and interconnected. So at the same conditions, you turn low viscosity dispersion into a gel. The same conditions, but total different properties. And you can even follow that by rheology, that you have changes in the mechanical properties, and this gives a porous structure here in these gels. And this is seen not only by cryo-SEM, but also by super-resolution fluorescence microscopy. Now, this is done here for the preparation at low synthesis concentration. Now we take the same polymer, which is prepared at high synthesis concentration, but diluted back to low synthesis concentration. So we have these vesicles. We start again, we cool down, nothing happens. We dissolve it at 5 degrees. So then it's basically the same what we had before. We have the same steps. We get these small micelles, and we get these worms in the end. So we get the same procedure, but we start from a completely different structure in the very beginning. And even the mechanical response is basically the same as before because it's the same polymer, but we started from a very different structure. So it's a very peculiar system where we have all of the 3 different structures, spheres, vesicles, worms, for the same polymer, and you can adjust it by preparation and by using a trigger. Now, if you don't like this thermo switch, you can also use hydrostatic pressure, because this blue polymer, this made of poly and isopropyl acrylamide and polyterpyl acrylamide, is also pressure sensitive. So this may be interesting also for the oil business, where you apply pressure and then the material liquefies, but if you release the pressure, it becomes jelly. So here's an example. This is at room or ambient pressure, and then you apply hydrostatic pressure, 1,000 bars, the material will disassemble in unimolecular dissolved chains, then you release the pressure, you get these micelles, and under certain conditions you even get these gels. So you get also back these jelly materials, these worm-like micelles. So I hope I could show you that non-equilibrium allows electrochemical manipulation to achieve E-micellization or E-microgels. And then I hope I could also show you that non-equilibrium state of micelles is beneficial because you can keep a certain system for years even. It doesn't change, but once you apply a trigger, it will run towards the equilibrium state, and major property changes are accompanied by that. So I want to thank my co-workers, my collaborators, the research funding, and I thank again you for listening and also for being here. I thank the organizers once more again. Thank you very much.